Alright guys, this is our last lesson for Unit 3. We're going to talk about how to do limits when you're dealing with non-removable discontinuities. So the answers for those are either going to be infinity, negative infinity, or does not exist. Now the only way we've really been looking at those before this lesson was on graphs, but we can actually be dealing with these things in the form of equations also, and so we're going to want to know how to deal with that when you can't see it on a graph. I'm also going to introduce you guys to probably for most of you, a new function known as a step function. And the way that we find the limits for those is very similar to the way that we find limits for non-removables. Well, that's because they are non-removable. And so we will talk about those as well. So let's go ahead and take a look at what a non-removable discontinuity is. As you guys might recall, a removable discontinuity is one where the limit exists even though the function is not continuous, and that's usually in the form of a hole or something like that. But most discontinuities are not removable, and so a non-removable discontinuity is a discontinuity that does not have a limit. And so the answer, if you were to try to find the limit, it would either be infinity, negative infinity, or it doesn't exist. And we have three different circumstances that we've already learned about that render non-removable discontinuities: vertical asymptotes, jumps, and oscillations. Okay, so for this one here, you can see that the limit from the left as x approaches c is negative infinity, but as x approaches c from the right, it's positive. And when it's opposite on both sides, then we just say it doesn't exist. Whereas over here, if it's infinity on both sides, then we can say that the limit is infinity. And then right here, if they're both going downwards, we can say that the limit is negative infinity. Now all three of those mean it doesn't exist, but that's how you would write it in each individual case there. And that's what vertical asymptotes do. Vertical asymptotes are pretty much the only ones that are going to give you a positive or negative infinity if it's a non-removable discontinuity. Jump discontinuities just simply don't exist because the limit from the left and right never match. That's what makes it a jump. And oscillations, their left and right hand limits don't exist either. Well, I'm sorry, the limit itself doesn't exist, and that's just because it's constantly bouncing around. So these are all non-removable discontinuities. These are things where the limit does not exist. So how will you know if a discontinuity is a non-removable one? Okay, because you're not going to really know just by looking right off the bat. Because even though, now like I said before, we've recognized them in the past by looking at graphs, but if we're looking at equations, it's a little bit harder to tell. You're not going to maybe be able to tell right away. And the answer is, well, if you've tried to remove it using factoring, rationalizing, simplifying, L'Hopital, if you've tried any of those things and nothing seems to be getting rid of the discontinuity, well, the chances are it probably is not removable, and so you probably have a non-removable discontinuity. And so at that point, we don't want to just say, okay, well, I'm done. We want to kind of go a little further, and we want to say, okay, so now more specifically, what am I going to say? Is the answer infinity? Is it negative infinity, or does it just not exist? Okay. Now, the only way that you're going to be able to determine that is by plugging in values that are really close to the given c value on the left and right, and just look at it. If you end up with a really big positive number, then you can assume that that limit is going into a positive infinity. But if you end up with a really large negative number, then you can assume that that limit is approaching negative infinity. Okay? So basically, we're just going to be looking at it from the perspective of tables almost again, but this time we're not going to plug in a whole bunch of numbers. We're just going to plug in one that's really close, and we're going to go with that as our answer, just to save some time. You could do a table though. All right, so for instance, take a look at this function here. Now just looking at that, if I asked you to find the limit from the left, the limit from the right, and the limit itself, how are you going to recognize that that's not removable? Well, first of all, if you try to do this, if you just kind of said, okay, well, that's easy enough. You should always try direct substitution first, but as you can see, that results in a problem. You can't have 0 on the bottom, so that's no good. Okay. So we know we can't do direct substitution, but as you guys know, that doesn't mean that the limit doesn't exist. That just means the function's not defined there. Okay, well, then I would start thinking about ways to remove the discontinuity. Well, direct substitution doesn't give me a L'Hopital form, so I can't do L'Hopital. And you'll also notice that I can't factor, because nothing here is factorable. You'll also notice that I can't do rationalizing, and you can't write that in a simpler form, so it's not a complex fraction either. None of our ways that we've learned how to remove discontinuities apply to this. It just seems that we're stuck, and you can't possibly find the limit. Well, that's a good indication that you probably can't remove the discontinuity. It's probably a non-removable discontinuity, which means that we either have an asymptote, a jump, or an oscillation. Okay? Now, let's go ahead and see what kind of a situation we've gotten ourselves into here then. So what we're going to do is I'm going to be approaching 3 from the left. So let's do that first. So if I want to approach 3 from the left, what I'm going to do is I'm going to plug a number in for x that is really close to 3. In fact, it's going to be 3 minus 0.001. I'm just going to pick 1/1000th. Now that's a random number, but I'm going to subtract from 3 0.001. In other words, that equals 2.9999. So what I'm going to do is I'm going to plug 2.9999 into this function here. So let's do that. What is f of 2.999? Well, you can do this with a calculator if you want to. A lot of these you'll probably need to do that. But by plugging in a number that is 0.001 less than 3, I end up with -1000. I would call that a really big negative number. And so what that tells me is that as I'm approaching 3 from the left, my limit seems to be becoming more and more negative. It's becoming really, really negative. And so what I would say then is I would say that the answer to this is -infinity. Okay? And you guys could test that. If you plugged in something even closer, like instead of plugging in 2.999, let's say you plugged in something even closer to that, to the left of 3, like that. You're going to end up with probably something like -100,000. So basically, as you get closer and closer to 3 on the left, this thing just explodes into -infinity. Okay? Now, on the right, let's see what happens. Now, notice this time it's plus. So that means I want to plug in numbers that are bigger than 3. So what that means then is I'm going to plug in some value for x that is more than 3, or to the right of it, in other words. And this time I'm going to plug in 3 plus 0.001. In other words, I'm going to plug in 3.001. So now let's do that. 1 over 3.001 minus 3. Well, that's 1 over 0.001. And if I do that division on my calculator or maybe in my head, I get a +1000. And so that tells me that as I'm approaching 3 from the right, from numbers that are bigger than 3, as I get closer and closer to 3, my y value is just getting bigger and bigger and bigger in a positive direction. And so that means that the limit from the right would be a +infinity. And as you guys know, when the limit from the left and from the right are not the same kind of infinity, then if you're just being asked to find the limit overall, then the best you're going to be able to say is does not exist, okay? Now, if they were both positives, then we could say positive infinity. Or if they were both negatives, then we could say negative infinity. But in this case, we can't actually do that, so we'll leave it there. So here is a student practice for you. You're going to need your calculator for this one. You're going to be plugging into ln. So Go ahead and see if you guys can evaluate these things really quick and see what you get. Okay, so here's our answers. So if I'm plugging in numbers to the left of 0, then I'm going to subtract from 0.001, which is going to give me negative 0.001. That's what I'm going to plug into this equation. And when I do, I get negative 13.8. Now that's a negative number. It's not that's actually not a very big one. But that's okay. It's still negative. We know that it's not defined at that point because if you try direct substitution, you're going to get ln of 0, which is undefined. And there's no way we can remove the discontinuity. So we can assume this is a non-removable discontinuity, and therefore we can assume that it is approaching either infinity or negative infinity. Okay. Now, in this case, since it's negative, we're going to say, okay, it's approaching negative infinity. And the same thing happens on the right, actually, and therefore we can say the overall limit is negative infinity. Now, if this wasn't satisfactory for you, then try plugging in something else. You know, instead of plugging in negative 0.001, try plugging in negative 0.000001. Try to get even closer to 0 on both sides, and then see what you get. And you're going to find that the smaller the value is, or the closer it is to the actual 0 that you're plugging in on the left and right, the more that the outcome is going to become bigger and bigger and bigger. Okay, but we'll stop there for now with that. Okay, so now we're going to do it with trig, and as you guys know, trig always throws in an extra layer of interest. So here we go. We want to approach negative pi from the right with this function here. Now, if you're using a calculator, you may realize that if you tried to plug in negative pi, it's going to say error. It's going to say undefined. And what that means is that the function is just not defined there. Cotangent actually has a vertical asymptote at that point. Now, that means that if I'm approaching negative pi from the right, it's either going up into positive infinity or negative infinity. So we have a nice 50-50 guess there, but we have a way to be a little bit more precise about this. Now, first of all, I want you guys to understand that if you ever have sine, cosine, or tangent, as a matter of fact, that's what your student practice is going to be. It's going to be a tangent one. You have a little bit of an easier job because those buttons are right on your calculator. But if you ever have cosecant, secant, or cotangent, you're going to need to change those in order to use your calculator because our calculators don't have cosecant, secant, cotangent buttons. So when you type this function in for cosecant, you're really going to type in 1 over sine. And when you type in a function for secant, you're really going to type in 1 over cosine. And when you type in a function for cotangent, we're going to type into our calculator 1 over tangent. That way, we can actually use our calculators by changing them into their sine, cosine, and tangent equivalents. Okay? So, having said that, let's go ahead and get started. So first of all, anytime you're doing trig, you got these pi's to deal with. And so I want to plug in a number that's really close to negative pi, but to the right of it. So first of all, that means I'm going to plug in x equals negative 3.14. Okay, so that's a number that is to the right of, or actually, you know what, let's go ahead and actually just use the real pi value, because since pi just kind of keeps going, that could be a little bit deceptive. So I'm going to plug in negative pi, but I want to add 0.001 to it, okay? So now for that, I'm going to need my calculator. Now, I almost put 3.14 for the pi, but you want to be careful with that because that actually rounds pi up or down, however you want to think about it, and we don't want to do that just yet because we're adding a really small number to it. So if you round it wrong, adding that really small number could mess things up. So let's go ahead and do negative pi, and your calculator should have a pi button on them, plus 0.001, and by doing that, I get negative 3.14, and I'll just put 1 there. All right, so that's what I'm going to plug in to cotangent. And now we run into a little bit of a problem, though, because my calculator doesn't have a cotangent button. But what did we say to do about that? We said, okay, well, that's all right. We're just going to rewrite it like this then. Okay, so let's go ahead and do that. I'm going to do 1 divided by tangent of negative 3.141. And then I'm going to multiply that by negative 2. And I end up with a positive number, which is 36. Now, that's not a horribly big number either, but since we know that we got an error sign and it's a non-removable discontinuity, it must be an asymptote, and therefore, if the number's positive, it must be going on up into positive infinity at that point. Okay? And so that's how we'll handle it. So first of all, when you're using your calculator on this, use the actual pi button on your calculator, and if you have secant, cosecant, or cotangent, don't forget to flip it over. But you don't have to do this reciprocal thing if you have sine, cosine, or tangent. Just use the buttons on the calculator as they are already. Okay, and so I'm going to let you guys practice one of these real quick. See how you do with this one. Go ahead and see if you guys can find the limit of tangent of x, or 2 tangent of x, as x approaches negative pi. Pause the video. When you unpause it, you'll see the solution. Okay, guys, so here's the answer. So we take our pi over 2, and we're going to subtract from it, because we're approaching from the left, 0.001. And so that means we're going to plug in an approximate value of 1.5697 or 8, maybe whatever you chose to plug in there. And then we're going to plug that into our tangent function and see what we get. I got positive 2007, which means that this function would be approaching infinity on that side. Okay? And so that's the little twist that trig functions can throw at us. And then we'll move on to our next part. All right, so let's go ahead and begin here with this example. This is an example I thought I would throw in here. It's relevant to what we're talking about today because this is a non-removable discontinuity problem. However, it's different from what we're doing today because every problem I'm showing you today requires you to use a calculator, but this was actually an FRQ question on one of the AP tests in the past, and it was not allowing the use of a calculator. So I just thought, well, it's kind of relevant to what we're talking about today, so I want to show you how we would handle it, so how you can answer these types of questions if you don't have a calculator. And what it really boils down to is you kind of need to know what these functions look like as a graph, okay? Now, on this particular problem, you can't just plug 0 in case you haven't noticed it. Ln of 0 is undefined, so you can't do that. So direct substitution is out, so we can't do that. But here's what I am going to do. We want to be aware of what the graph of ln of x looks like, and I also want to be aware of what the graph of 1 over x looks like. Okay? Why is that? Well, because really this limit is really just those two functions put together. Another way to write this would be like this. Ln of x over x is the same thing as ln of x times 1 over x. And since we have that, we can use our properties of limits to take the limit of each one separately. So I could take the limit of ln of x, and I can also take the limit of 1 over x as x approaches 0 from the right. Okay? But I'm going to evaluate each of these by looking at their graphs. So what does the graph of ln look like? Well, the graph of ln looks like this. So if you didn't know that, then you wouldn't be able to answer this question. But that's what ln looks like. Now, if I'm approaching 0, from the right side, it looks like we're getting to negative infinity. So this one's negative infinity. What about 1 over x? 1 over x is another odd-looking function. It looks like this. It has two pieces to it. Now, if I'm approaching 0 from the right, that's positive infinity. Well, negative infinity times positive infinity is negative infinity. Okay? And so that's how you would do that one. You would look at the graph. So sometimes knowing what the shape of a graph looks like can be very helpful if you want to do limits. and you don't have a calculator available. All right. Let's go ahead and move on to the next part. So we're going to switch gears now. We're going to introduce you guys to a new function called the step function. It's also known as the greatest valued integer function. It looks like this. Little brackets here. Now, how this thing works is that when you plug a number into this type of function, the output will be the greatest integer that's less than or equal to the value in the brackets. Now, that's a mouthful. I would have to read that sentence about 3 times before I fully understood it. So let me give you an example. Okay? So suppose I were to give you guys the following number here, and just plug this number in really quick. Let's say I gave you 5.63. All right. Well, first of all, you need to know what an integer is. An integer is a number that has no fractions in it. No decimals, no fractions. Just a solid number like 1, 2, 3, 4, 5, 6. It could be negative, but no decimals or fractions. That's it. Okay? So when you plug a number that is a fraction into the greatest valued integer function, what it's going to do is it's going to change the number into the greatest integer that is less than or equal to this number. So what is the greatest integer that's less than 5.63? In other words, what is the integer that is, should we say, I want to say to the left of this number, but it's not always the case with negatives, so that can be confusing. But the answer is 5. The answer is 5. So the integer that is less than this number, the greatest integer that's less than, there's a lot of integers that are less than 5.63, right? 5 is less than 5.63, 4 is less than 5.63, 3 is less than 5.63, but we want the greatest integer that is less than 5.63, and the answer is 5. So let's do another quick little example just before we go on any further. How about this one? What would be the greatest integer that is less than or equal to this b? It would be 9. Okay? So there's the idea. Okay? Now, example 2. Funny things happen whenever you get into negatives. Now, what's the greatest integer that is less than or equal to negative 9? Right, well, I would imagine some of you guys will guess 9, but here's the problem. Negative 9. Negative 9 is not less than negative 9.271. It's actually greater. Remember, negatives are opposite, so negative 9 is actually more than that. So we want to know what is the greatest integer that is less than this one. Well, let's list a few. Like negative 10 is less than that, or negative 11 and negative 12. What's the greatest integer that is less than negative 9.271? And that one would be negative 10. So you got to be careful with the negatives. They kind of flip the game on us. I guess maybe a nice cheating kind of way, a nice way to kind of cheat this and make it less confusing is in the following way. If you have a positive number, always round it down no matter what. If you have a negative number, always round it to the next negative farther to the left, the more negative number. Okay? So that might be a good way to kind of think about that. Okay? Now, it's possible that you just plug an integer into it. Like, let's just say I plugged 9 in. Well, if you plugged in 9, the answer is just going to be 9. Okay? Because it doesn't change it at all. All the greatest valued integer function does is basically it rounds out the fraction values. Anything less than 1, like a fraction value, just chops it off and just rounds it to the next nearest integer, basically. But if it's already an integer, then nothing happens. It just stays the same. Okay? So, if you want a little extra practice, I'm going to give you guys a couple of problems here and see how you do with them. You don't have to do this if you feel like you've already got it. Go ahead and pause the video here and see if you guys can guess what these would be. So the answer to example 1 here would be 2. The answer to example 2 there would be -4. And the answer to this last one here would be 6. And that's it. Okay? So that's the idea. So here's another way to think about it. I'm still introducing the concept to you. I'll show you. We're going to get to limits of these in just a minute, but just want to make sure you guys have fully got it. I'm going to make a graph this time. Now, any number that is from -2 up to -1, the answer is just going to be -2, right? So, for instance, if you were to plug in -1.5, that's a number between those two values, it's going to get rounded to the next integer that is less than -1.5. That'd be -2. So, from -1 to -2, the answer is always going to equal -2. So from here up to, but not including this point, it's always y equals 2. Then something happens. As soon as you get to -1, you're in a new domain. You're in a new area. From -1 up to 0 on the x-axis, the y value will always be -1. So from -1 up until I get to 0, the y value will always be -1. And then from 0 to 1, the y value will always be 0. And then from 1 to 2, the y value will always be 1. And then from 2 to 3, the y value will always be 3, and so on. And so you end up with this thing, and now you guys can see why they call this a step function. It kind of looks like the steps of a staircase, doesn't it? Okay. Now, as you can tell by looking at this graph, if you're trying to find the limit at an integer value, you're going to have a problem, right? Because anytime you get to an integer, the limit from the left and the limit from the right are never going to meet up. That's a non-removable discontinuity. Okay. Now, if I ever asked you guys to find the limit of a point that's in between two integer values there, like right there, for instance, well, you're going to get an answer. There's nothing fancy about it. You're going to get a solid answer. But if you ever want to find the limit at one of those step places, where it goes from one level to the next, the answer is going to be no solution, but we need to prove that. We need to show our work for that. We don't want to just assume it, because what if they actually do give us a point where there is an answer? So we need a way to just get an answer and know whether we're here or here, whether we get an answer or not, right? So now we're going to go ahead and apply what we've just learned about step functions with limits and put all this together. So we will evaluate the limits of step functions by plugging in numbers that are very close to the given value. And then we're going to round that value according to the definition of the greatest valued integer function. And that will give us our answer. Okay? So here is our first example. Let's go ahead and take a look at it. All right, so here's my function, and I want to approach -3 from the left. Now, as I've mentioned, when we're doing step functions, we're going to treat these like they're non-removable discontinuities, because they very well may turn out to be that, okay? And so what we're going to do is we're going to plug in x is equal to -3 minus 0.001, just like we did with the other one, right? And so that's actually going to give me -3.001. I'm going to plug that in for x into this function, and I'm going to see what I get. So let's go ahead and work that out. All right. Now I'm going to use my calculator for some of the steps here. Now what I get as a result is 5.006001. Now, what is the greatest integer that is less than or equal to this? Well, the answer would be 5. And that's going to be my answer.
All right, I just uploaded my answer.
All right, let's do it again for the next problem. So for my next problem, I'm going to plug in a number where x is equal to negative 3, but this time plus 0.001. And I'm going to get negative 2.999 if I do that. So let's go ahead and plug that in and see what we get. And once again, I'm going to use my calculator. And I'm getting 4.994001. And that's a positive one, right? So when we round the positive ones, we just chop off everything after the decimal. And we've got our answer there, so that's 4. So the limit from the left is 5, but the limit from the right is 4. And so this must be one of those places where x, where the function jumps from one value to another. Now, if we were doing this, though, and we actually got the same answer for both of them, well, what that would mean is that the limit actually exists, and it wasn't actually at one of the step places. It was somewhere in between, in the middle of the steps. Okay? But in this case, we would just say the limit, therefore, does not exist. All right? So let's go ahead and have you guys try one. Go ahead and pause the video here and see what you get. Okay, so there you guys have it. For the first one, I would plug in 4 minus 0.001, which is 3.999. And by doing that, we get 2.998. And then if you do the greatest value less than or equal to that, you would end up with 2. And if you plug in the next one, for number 2, I'd plug in 4 plus 0.001. And when you do that, you get 3.002. And the greatest integer less than or equal to that is 3. And so the limit from the left of 4 is 2. The limit from the right of 4 is 3, which means that the limit doesn't exist here once again. Okay? And so that's how we evaluate limits of step functions. And that's going to close out our lesson and also close out our Unit 3. And so the next couple days we'll be doing some studying, getting ready for our test, and we'll see you guys in class. Bye-bye.